just joining, welcome to the ECR Forum of the Supergen Net Zero Conference. We are starting now. I must say that we are recording this session, so if you are speaking or presenting and you would not like the recordings to be shared afterwards, please just let us know via email. My name is Dan Taylor and I'm the COP26 Engagement Manager for the Supergen at the Supergen Bioenergy Hub. I've helped organise this session with our cross-hub ECR group, one of whom is Santosh Kumar, who is going to be chairing this first hour-long session on greening the economy and society. So over to you, Santosh.
Thank you, Daniel. Hello, good morning, everybody. We are excited to bring this cross-hub event, early career research event within 3 days of Net Zero Conference ahead of COP26. And let me start thanking our organizing team, particularly, we have a team of 6 members, but particularly Dan, who has, done an excellent job in coordinating all the 6 energy-related hubs and making this happen, particularly. We also have Rachel from Super Solar and Ajit from Offshore, and Amrita from Energy Storage Hub, and Ola and Kevin from Energy Network Hub, and myself representing Bioenergy Hub, Supergen Bioenergy Hub, and also voluntarily representing hydrogen because we're missing representation from Hydrogen Hub. As you all know, the structure is 30 minutes panel discussion and 5 minutes flash talks on greening the economy and society and the future of sustainable transport and securing a global transition to clean energy. And particularly, I'm going to chair this session, the first session, that's greening the economy and society. In this session, we particularly have 3 flash talks. The first flash talks given by Ahmed Gilani from University of Leeds, and then the second flash talk, Jonas Sparks from Austin University, and third one is Kasper Stefnek from Catpulse. So then followed by the 30 minutes panel discussions. Further, we joined by Samuel Perry and Evelyn from Centrica. Samuel is from University of Southampton. So so without, I think, let me also thank you all, the speakers and as well as the participants and making happen on this wonderful event. And yes, with this, without wasting my time, your time, and I would like to, invite our first flash talks speaker, Ahmed Gilani, if you are ready.
Hi, Santosh. Thank you very much. Thanks to Dan and the team as well. I'll just share my screen if I may. Okay?
Yeah, that's good.
So can you see my presentation now?
Yes, we can see. That's great.
Okay, thank you very much. So my name is Ahmed Gilani. I am the Research Fellow of Industrial Decarbonization at the University of Leeds. And my presentation title is Assessing Net Zero Pathways for UK Industry. So this is part of UK Energy Research Centre project. So let's get started. So my presentation is divided into 4 main parts. I'll give a brief overview of the UK industry and the net zero pathway models that we are using to assess the net zero reductions, emissions, and then I'll provide some sensitivity analysis for the key parameters that we're using, and then conclusion remarks. So as you know, industrial projects are essential for daily life and economic growth. So the number of jobs employed in these sectors, such as chemicals, iron and steel, and food drink, cement, oil platforms, these are around 7 million jobs directly or indirectly. Yet the industry is difficult to decarbonize. Actually, it's very difficult compared to power sector or transport sector because we have inhomogeneous products and processes that if we change even if we change the fuel, of that process, it is not guaranteed that it will be competitive or it would work. So that's why the industrial sectors are highly emitting, producing 16% of UK emissions. Now, industrial sector modeling or energy research modeling in general plays a major role in informing government policies and developing net zero industrial pathways. So most of the government's actually policies are based on modeling. One such model that we are using is the NZEB model. It was developed by Element Energy for the CCC6 carbon budget and used to underpin the analysis for the industrial sector. Now, NZEB is a special, as you can see here, there are around 6,000 sites divided for all the UK, and then for each of these sites, they have some industrial process, and we want basically to decarbonize these processes. So we are estimating what is the best economic option for their processes to be in line with net zero by 2050. One example output from the NZEB model is like this, which is here is the route to net zero for all UK industrial sectors, and which are the technologies used to decarbonize the industrial sector. So we can see that re-measures, electric, blue hydrogen, and CCS plays a vital role till 2050. So what we are doing is that we are assessing the sensitivities for some of the key model parameters and explore the impact, on the decarbonization base, the decarbonization technologies used, the investment costs, and the fuel use. So we have changed much of the model parameters, but I'll focus on just two: the carbon price trajectory that is assumed in the model, and high and low temperature heat process decarbonization and their role, in achieving net zero. So if we see that the pathway to net zero in this graph to the left, we can see that the industrial pathways are highly sensitive to carbon price. So lower carbon price will not abate much of the emissions that we want, while higher carbon price can, push the net zero pathway from as early as 2035 and on. And then we can see here that resource efficiency and energy measures, along with the CCS, plays a vital role together with electric and blue hydrogen to reach net zero. If we compare high temperature heating processes and low temperature heating processes, we can see that here, like for high temperature heating, we want CCS, carbon capture and storage projects, but for low temperature heat, we rely on blue hydrogen, electric, and resource efficiency measures. But if we concentrate the CCS, then there's no alternative for high temperature heating, so there will be remaining emissions there. So in conclusion, net zero pathways for UK industrial sector is highly sensitive to carbon pricing, and re-measures along with CCS, electric, and blue hydrogen technologies play the most critical role in industrial decarbonization by 2050. This is at least what the model is telling us. And then finally, a net zero consistent pathway for UK industrial emissions require heat provision, so particularly high temperature heat processes to be almost completely decarbonized. Now, I thank you for listening. Can anybody hear me? I'll unshare if.
Oh yeah, thank you, Ahmed. Sorry, I was muted. Thanks a lot for your excellent talk. The next talk is by Jonah Sparks from Aston University. Yeah, screen is yours, Jonah, if you're ready. And you're muted, Jonah. So just a small announcement before you start. The Pamela is happy to talk as well. So so basically the flash talks will go as settled before. Thank you so much.
Great, thank you. Can you see my slides now?
Oh yeah, I can see. Yeah.
Great. Okay. So hi, everyone. My name is Joanna. I'm the Biomass Policy Fellow at the Supergen Bioenergy Hub, and I also work with these 3 networks that are shown here. So I'm going to talk to you about greening the economy and society through the use of biomass and bioenergy. And the way I'm going to present this is a little bit different, because I'm going to talk about some of the key points from our recent submission to a government call for evidence around the use of biomass for net zero. So bioenergy is one route by which we can reduce our greenhouse gas emissions, and it does have the potential for negative emissions if it's coupled with carbon capture and storage. So it's obviously a really important part of that net zero transition. Biomass also has non-energy applications, and that means that it can help to decarbonise other sectors or other parts of society as well. So biomass supply and utilisation has the potential to create sustainable new industries, to create new supply chains and to create new jobs, and it can also contribute to a circular economy. However, achieving this potential will require further research and innovation, as well as support through policy. So the first thing that I'm going to talk to you about is the supply of biomass, which is really important if we're going to use it for lots of different things. Despite concerns that the limited amount of biomass we have means that we can't do all those things that we want to do, research and modelling, including work done by the Bioenergy Hub, has shown that we are not yet constrained. The UK actually has the potential to produce a lot more sustainable biomass than we currently do, without impacting food production, if appropriate policies are put into place. On top of this, we have to think about the fact that there are a lot of different biomass feedstocks that we could use. The growth or supply of each of these feedstocks comes with its own potential sustainability issues or impacts, but also potential benefits. There's a lot of work going on in this area to really understand. So, for example, to map where the biomass might be across the country, to understand how much we have, to understand what those benefits or impacts might be, and to minimize and to think about how to balance them. And then also to think about how we use all that information when we're making decisions, for example, around land use. So the next thing to talk about is what we actually use the biomass for. So research has developed loads of different ways that biomass can be used for energy, as well as all those non-energy uses that I talked about before. So how do we know which application to use the biomass for? Decisions around what to use biomass for should take into account the greenhouse gas savings that can be achieved compared to the system as it is now, but also consider how hard the sector is to decarbonise in other ways. So the third thing to think about is sustainability, and this is a really big topic at Supergen Bioenergy Hub. When we talk about sustainability, we're thinking about more than just greenhouse gas emissions. Sustainability includes wider environmental impacts, but also societal and economic aspects. It's important that wider sustainability issues are understood. Benefits in one area are likely to have impacts in another, so well-informed decision-making is essential if we want to be truly sustainable. The final thing I'm going to touch on is technologies. We all know that there's no silver bullet when it comes to decarbonising, and this applies within bioenergy as well. There are numerous technologies that can be used in bioenergy systems, many of which are researched at the Supergen Bioenergy Hub. All these technologies are at different technology readiness levels. Some of them are suited to certain feedstocks, some of them are suited to certain end uses. On top of this, different technologies may need to be coupled or integrated to achieve the goals that we have. Further research and innovation is needed to develop these technologies, but we also need more support for scale up so that we can actually make use of the technologies in trying to achieve our net zero targets. So thank you for listening, and I hope that has inspired you to come to the Bioenergy Hub session later in the week and take a look at our call for evidence response that's on the website. Thank you.
Thank you, Jonah. Thanks for a nice talk on bioenergy role in delivering, sustainability goal. I think Jonah will be joining the panel discussion, so we will be able to comment more on this as well. So the next talk, last talk, is by Parimala Prasad, University of Bath. The screen is yours, Parimala.
Thank you very much, Santosh. I hope everyone can see the slide and can also hear me.
Oh, yes, we can see.
Brilliant, thank you. Very good morning, and thank you very much for the invite once again. I'm Parimala Shivaprasad from the University of Bath, where I'm currently a research associate. And I'll be speaking a bit about my research and also my spin-out company and our aim towards contributing to net zero and decarbonizing the chemical sector. So so globally, there's an increase in demand for naturally produced chemicals over synthetic chemicals. So industries are looking for a chemical-free route and trying to replace chemical routes with biocatalytic routes. However, globally, the revenues for the synthetic chemicals still surpass that of the natural chemicals. And this was mainly attributed to the lack of technology or lack of raw materials, and also high cost of manufacturing the natural chemicals. And one of the key challenges brings us back to the current ways of manufacturing fine chemicals, especially as we're still using batch reactor technologies, which have challenges associated with scale up and inconsistencies in product, and also not being suitable for shear sensitive catalysts like enzymes. And hence, there is a need, or there's a shift towards finding novel reactor technologies which can achieve production of chemicals in a more sustainable and a more greener way. And this sort of feeds back to the opportunity where the UK imported more than 200 million of cosmetic chemicals within the fine chemical sectors from outside the country, both EU and outside of the EU. But as we all know, there's Brexit, there's been supply chain disruptions in terms of the pandemic as well. So the UK's vision for 2050 is to make manufacturing more resilient, local, and hence they're investing a lot in in localized manufacturing technology. So basically flexible, modular, and scalable technologies to make manufacturing possible in-house. And also sort of looking at how can we use this technology to solve some of the global challenges. I come from India, where we have a lot of flowers, and India produces close to 3.5 tons of flower waste. And so that's where sort of my research goes into, as to how can we use this flower waste, or can we come up with a technology which can produce or valorize the flower waste into some useful chemicals. And so in my research, we've developed a novel catalytic reactor known as a spinning disk reactor. So if you can imagine a record player which spins at a really high speed, and the disk also has a cloth resting on top, and this cloth has the catalyst attached to it, which makes reactions happen faster. So the disk and the cloth are spinning at a high speed, and then we inject a liquid feed onto the center of the disk, and this causes a thin film on the surface of the cloth, and this increases the contact between the catalyst and the liquid feed. So hence we have faster mass transfer and hence faster reaction rates, and we're able to make the products much faster compared to a traditional batch reactor. And this is the prototype of the SMDR we have at the university. And these are just some results from my previous research, where we've shown the increase in conversion compared to batch, and how we are able to reuse the catalyst cloth multiple times. And also we're able to save more than 30% in terms of the raw material cost, especially with the catalyst, because we are able to reuse it multiple times. And so towards the end of my PhD, I was really keen on exploring the commercial opportunity for the SMDR, and so I was a graduate of the IQR program, where I carried out a global market research, and this led to incorporating SMDR in 2020. So as a company itself, we are looking at producing, or we're collaborating with pharmaceutical companies to manufacture APIs. But this is a part of my independent research, where I'm looking at valorizing flower waste, and this is also a social enterprise in India. But then I'm looking at how can we valorize or transform secondary alcohols into cosmetic chemicals, or for the food and the pharmaceutical industry as well. So this is a project which is funded by Innovate UK, RANG, and EPSRC, and I'm also collaborating with research in Malaysia and Edinburgh to make this happen. So just a few people to thank, and thank you very much.
Thanks a lot, Pamela. Excellent talk. Yes, moving on to our fourth flash talk by Kasper Stefanek. If you're ready, your screen is yours, Kasper.
Thanks a lot. Just give me a second.
Yeah, we can see your screen now.
Great, thanks a lot. Morning, everyone. I'm Kacper Stefaniak, and I'm a strategy analyst in Offshore Renewable Energy Catapult. Our Catapult is a research center based in Glasgow and Blyth, and today I'm going to talk about offshore wind. First of all, what's the reason behind the hype for offshore wind? There are two or maybe three main factors. First one is the load factors, which is the resource availability and in general how much energy we can produce from an energy source. As you can see on the graph on the left, offshore wind installed in 2019 had 39%, but the wind farms that will be installed in around 3 years' time will have even 58% load factor, comparing to 72 by nuclear. Offshore wind load factors in the UK has the highest from all renewable sources. This is mostly due to the more consistent winds and higher speeds. Secondly, the cost of offshore wind. We've seen the levelized cost of electricity in the UK to decrease by 70% in 15 years, and they will reach wholesale electricity prices by 2024. Just for your reference, the new build nuclear power plant will cost 93 pounds per megawatt hour. And thirdly, in the UK, we are lucky to be an island and to be surrounded by a lot of sea where we can build out offshore wind. We've conducted an analysis where we've tried to measure what would be the maximum realistic deployment of offshore wind by DNO zone. This analysis utilized GIS modeling, including relevant technical, environmental, social, and techno-economic constraints, in order to calculate the maximum installed capacity of offshore wind by 2050. And we came to a total number of 600 gigawatts, which comparing to what we have installed right now, which is around 110 gigawatts, and by 2050 it will be around 278, means that only offshore wind could satisfy electricity consumption more than 2 times. This is an abundant source of energy for the UK that we can not only use for electricity, but also for exports. As you can see in the future energy system, will mostly shift from fossil fuels to renewables and nuclear, from 48% in 2019 to 75% in 2050, and the installed capacity will at least double. It will have its own flexibility challenges. That's why interconnectors and hydrogen support will play the key role in supply side flexibility. By 2050, we are legally obliged to reach the net zero emissions, and energy sector is, to be honest, one of the easiest to decarbonize. Apart from energy sector, we also have buildings, industry, transport, and land that will be more difficult to decarbonize. It will require replacement of natural gas for heating, oil for vehicles, and different zero carbon alternatives. If there is an affordable source of zero carbon electricity, a majority of heating and personal transport is likely to be electrified. This means that net zero will touch on possibly every aspect of our life. It's not only about the energy sector, but also others. Thank you, everyone.
Thank you, Kacper. That's a great overview of offshore energy work in a short time, 5 minutes. Thank you so much. So now the session is basically open for the panel discussion. Hopefully, we are also joined by Samuel and Evelyn as well. And let me also remind you, all the participants, so don't worry if you are not in the panel list, but still the chat box is open. You can text your questions, or you can continue the discussion within the chat box as well. But yeah, just to tell you that, so just respect the each other views and debate constructively. That's all we'd like to see basically. Right. So I would like to hear how diverse we are. If you introduce in brief yourself. If I can start with Jonah.
Hi everyone. Yeah, I'm Joanna. So as I said in my presentation, I'm the Biomass Policy Fellow with the Supergen Bioenergy Hub. But what that means is I work with members of the hub and those 3 networks that I'm also employed by to help them communicate with government and also kind of communicate back from government to the academics and the research community.
Thank you, Jonah. Ahmed?
Oh, hi. Yeah, my name is Ahmed Gailani, and I am the Research Fellow in Industrial Decarbonization at the University of Leeds. I am part of the UK Energy Research Centre projects, and we work with the University of Bath, BASE, and the CCC.
Thank you, Ahmed. Evelyn?
Good morning, everyone. I'm Evelyn Heijlen. I'm a researcher at Centrica Business Solutions. Besides that, I'm a visiting researcher at Imperial College, working in the field of power systems and demand-side response and IoT assets.
Samuel?
Yep. Hi, everyone. My name is Sam Perry. I'm a research fellow at University of Southampton. My background is electrochemistry, mostly sensing and catalysis. And recently, I've been looking into the electrochemical conversion of CO2 into value-added materials. So this covers industrial relevant materials and also biofuels as well.
Thank you, Samuel. Casper?
Morning again, everyone. I'm a strategy analyst in Offshore Renewable Energy Catapult. I'm mostly focusing on various road mapping activities and different net zero projects that involve green hydrogen and future energy systems.
Thank you. Pamela?
Hello, everybody. I'm Parimala from the University of Bath, where I'm a research associate, but also director of SMDR Limited, which is a spin-out from my PhD research, where we're trying to make pharmaceuticals more faster and greener using a novel catalytic configuration.
Thank you so much, all of you. So we have a nice, diverse, panel team from industry and academia, and also, policy. That's great to see all you here. So I would like to, start with asking you a question, particularly, the net zero target. So is net zero target that's basically 2050 is too ambitious to achieve or achievable? So I would like to hear your personal view on this. So anyone can start voluntarily.
I can go first then. I believe that this target is not only achievable, but also is not ambitious enough. I believe that we definitely can achieve it faster, but only if we will give the climate crisis the crisis lens. At the moment, we are mostly giving out targets, putting them as ambitious, but not really developing roadmaps and actions for the next 10, 15 years. So just putting a target in 30 years doesn't mean that we will successfully decarbonize our economy and society.
I will jump in and add, I agree with what Casper just said, and I think I heard one of I think it was one of the chief scientific advisors for BASE recently got asked basically this question and said it's not really about whether it's achievable, we don't have a choice. And so yeah, I agree, it is achievable, but we have to really treat this as a crisis, and we have to put appropriate policy measures and do the appropriate research to actually get there and really speed things up.
Yeah, I agree with the Casper and Joanna, and I think we as researchers, particularly electrical researchers, have a duty, I mean, to give the public the impression that we are facing a real climate change crisis. So, for example, in one of our papers recently, we said we need to avert more dangerous climate change. That means the climate change we are facing is really dangerous, and we want to avert a more dangerous one. But I think the government policy is somehow slow, particularly regarding, the large infrastructure projects such as CCS and hydrogen that are necessary to decarbonize the industrial sector.
Yeah, I mean, those are valid point. I would like to, hear as an early career research community. So, what is our role, today, in order to deliver this net zero target?
Yeah, I think it depends a bit on like the research direction that you're working in. Like if you look at the field of power systems, there are some technical challenges or technological challenges that we are facing. We have the phase out of synchronous generators, which causes some technological challenges in keeping the system stable. But yeah, the solutions are being developed, and it's possible to solve these or to deal with these challenges. So if you look at the power system perspective, there we have like the development of new control strategies, both for the inverters of the PV plants, batteries, storage assets. And on the other hand, we have also the development of like the control of, for instance, these smart devices at homes, and how we can incentivize people in really participating in this type of programs where we try to keep the balance between the uncertain supply of energy from wind and solar, and then the demand by steering, for instance, demand for heat in the houses. So from that perspective, that's my insight in the research that is currently going on.
Yeah, if I can just quickly add to that, Santosh, and also sort of answer one of the questions which just came up in the chat by Thomas about the value of case studies. And I guess as a researcher who's trying to, researcher to an entrepreneur trying to implement research on an industrial case, I think the most of the feedback we got from the industry was, okay, so you can do this for your simple model reaction, your reactor works very well, but can you actually make us this product which can cost less than the batch reactor? So, and I guess that's exactly what we're trying to do, is take commercially important reactions and scale them up in our technology and show that it's much better than the existing technologies. And I guess that has a very strong, that's going to build a really strong case for when we want to implement research or see, the change happening on an industrial level as well.
So anybody else would like to comment on that? Yeah. And also, so your research perspective in your field, so like how do you feel, so an early career research and today's role in delivering, net zero targets? It's not I mean, necessarily, in a broad perspective, but also in your whole field. So, how do you feel yourself? If you could comment on that. Anybody else you wanna say on that? So we also have a question from the Patricia, also Bioenergy Hub Director. She says, so the session started with an overview of modeling and its role in policy. I would be interested in the view of panelists on whether they think our current use of such models adequately reflects their different technology areas and provides a robust basis for decision making.
For me, I mean, I speak as we are using a model that covers the whole UK industrial sectors, a bottom-up model that covers around 6,000 sites. And it is geographically special. So, for example, sites in the north will probably have some access to infrastructure that is different from site to in Southampton, for example. I see these models are giving only an indications of what is going to happen. There are a lot of uncertainties that maybe it's invalidated, but we believe that all models are wrong, but some are useful. So the model that we are using is somehow useful to give an indication of what we're gonna need in terms of the infrastructure for like hydrogen and CCS infrastructure for industrial decarbonization, and that drives government policy and the private sector investment. So I see the models are useful, but they are not completely right.
I think I agree. Just to add on this, we're frequently collaborating with different energy system modelers, and what we found over the years is that not all the cost and load factors are updated as frequently as they should. And for renewable energy sector, it's absolutely essential, because the cost of, for example, offshore wind 5 years ago is really different to what it is right now. It's same with green hydrogen, but also we've seen some numbers on blue hydrogen being slightly too ambitious. So I believe that those models are absolutely necessary, but we need to make sure that all the data that we input to it is as up to date as possible.
Yeah, that's a valid point. And also, like, do you think is government considering all the stakeholders into consideration in this pathway to net zero?
Santosh, can I be cheeky and jump back in on the modelling question before we move on to that?
Yes, please. Yes, of course.
Since Patricia asked it, I feel like I should answer as the Bioenergy Hub person. Yeah, so I think that the other thing, and I hope that none of the Bioenergy Hub modelling people jump on me for this afterwards and that I've got it wrong, but I think part of it is about what model you use for what thing, because there are different types of model that do different things, that take into account different things. And it's about which model you use for which bit, and how those different, you might need to use multiple models for one set of decision making to take into account different things. On top of that, I think there is, even bioenergy, there's a need for more research and more modelling, because you need to go into more detail on certain things and figure out how those different models can work together to give you the information that you need.
Yeah, thanks for so your point. Yeah, so as I said like earlier, so is it, I mean, something I'm wondering, whether the government is taking consideration of all the stakeholders in this pathway to net zero. So what you see, as a researchers, as a legal researchers, how do you see the government strategy on this? And also, like, one of like the government is looking not solo, but one of the the key strategies is hydrogen economy. So I see, I mean, that's great, hydrogen, as long as if you produce hydrogen via renewable sources, it's great. It seems there is a future. It can dominate the energy industry. But the current, if you look at the current scenario, so the most of the more than I would say, more than 80% hydrogen is produced using fossil fuel sources. This is something first we need to address. Basically, we need a process where we can produce hydrogen renewably. The only I can see is solar, and I can also see electrolysis, but these processes are very expensive. So how do you? I mean, do you think, like, I mean, during our journey to net zero, do you think we can come up with a technology which can produce hydrogen using renewables? Are we so what is your opinion on that? Yeah, so I can. Daniel, can you let Team Mace to in the panel to speak, because he raised a hand. He want to ask question or maybe want to say something. Can you allow him to, Daniel?
I can do that now. Give me a second.
Yeah.
Tim, you should have the ability to use your microphone and even put on your camera.
Good morning.
Good morning.
Good morning. Hi, Paramala. Nice to see you again. I'm a member of the Hydrogen Fuel Cell Supergen Hub, and I'll be attending the sessions later on. But I thought if I may mention about hydrogen as this has come up. I think the comment about hydrogen from fossil fuels is well made. It is unsustainable in every sense of the word. It produces CO2. It's a high temperature process, high pressure process, and cannot continue in the long term as a source of hydrogen. I think renewable electricity, including new techniques like photocatalytic water splitting, have a lot of potential to produce hydrogen at scale sustainably. Yes, there are efficiency issues that need to be resolved, but that can be mitigated by using excess electricity that otherwise would be wasted. So you could argue that is a counter argument against the inefficiencies that currently apply to electrolysis. So I think that there are genuine opportunities for hydrogen production at scale using some of the technologies I've just mentioned. So I don't want to say much more because this is an ECR session and I'm at the opposite end of my career. Thank you.
Thank you, too. That's good to hear from you as well.
I'm happy to jump in as well, actually. But I'm going to do a double whammy because I know you asked a question about stakeholders before, so I'm going to answer that first and then I'm going to talk about hydrogen, if that's all right. I think that it probably varies from sector to sector, how stakeholder engagement is going. I think one of the things that has come up recently that I thought it was worth mentioning is the wider public, the individual, taking into account the individual when we're thinking about net zero. If our net zero strategy puts an emphasis on people changing their behaviour, we have to think about what that actually means for the different parts of society. If it's going to be expensive to do those things, is everybody going to be able to do it? If you live in a rural area, is it the same for you to do it as someone who lives in a city? And I think that one of the ways that we tackle that is by talking to people, but also including social scientists in the decision making and the research that we're doing. So that's the stakeholder part. In terms of hydrogen, I think it's worth mentioning biohydrogen as well. So hydrogen from biomass. Biomass has loads of hydrocarbons in it, and we should be thinking about how we strip some of that hydrogen off, use the remaining hydrocarbon as a way to produce fuels or to produce chemicals, and then use that hydrogen. I don't think that biohydrogen will ever be our main hydrogen source, but it is another green route to hydrogen that we should be thinking about. And really, as we move to 2050, we shouldn't be considering other like fossil-based routes to hydrogen at all, in my opinion.
Yeah, no, that's a valid point. Even I think for now, like the government mostly invested in electricity based fuels. If you take the transport industry, they mostly invested in electric cars and so on. But it's also important to focus on hydrogen and fuel cell. I mean, hydrogen is not a direct fuel, but it's a carrier. So hydrogen-based fuel cell technology, there is a potential. I mean, not only transport, but also in heating up buildings. So can hydrogen play an important role as well? You may agree or disagree, but I feel there is a scope in using hydrogen in that sense. But the thing is the safety. So safety is something need to be investigated and taken into consideration, and also the skills gap, I guess. That's as you're saying. So like bringing social scientists and collaborating, and then that reducing that gap is something is key. Centralized and decentralized hydrogen economy. So when it comes to industry, so like which industry do you feel is hard to decarbonize, and what their role in this pathway to net zero?
If I may, for me, I think that the cement, the cement sector and in the industry is difficult to decarbonize because there are no cost-effective ways to produce cement without using fossil fuels. And also in our models, waste incinerators, so waste processing sector is also difficult to decarbonize without using carbon capture and storage. So there are a lot of processes that we notice in the model that for now, the only way to decarbonize them is to use CCS or BECCS, or bioenergy.
Yeah, I think So but yeah, bioenergy is looks promising in combination with carbon capture and storage technology. But there are also questions, on use of the sustainable feedstock, and in the competition with the food industry. So, Jonah, would you like to comment on that?
Yeah, so I mean, first I'll talk about the hard to decarbonize sectors, because this is something we think about quite a lot in bioenergy, because obviously there's other technologies, there's wind, there's solar, all these things. And so when you're thinking about where you're going to use your biomass, part of what you want to think about in that decision is how can we decarbonize this sector in other ways? If it's really hard to decarbonize something by making it electric and using solar or wind, then maybe biomass plays a role there. So it's something that we do think about a lot. So a couple of areas to mention, I think, is transport, and I don't mean road transport. I know there is biofuels in use in cars at the moment, but we're obviously heading towards electric vehicles in that area. But shipping, heavy freight, aviation are all things that, particularly in the short to medium term, are going to be really hard to electrify. And so in intermediate, until we manage to make those electric or switch them to hydrogen, biofuels are going to be really, really important in reducing the emissions from those sectors in the short term. The other thing to mention is, for example, off-grid or rural areas that maybe are quite different to what we're all used to thinking about in a city or in an industrial park, where they don't have gas grid, they don't maybe have electrical grid. And so those areas can be quite hard to decarbonise, and that's another area where biofuels are likely to have an impact. Thirdly, waste, I think, was mentioned then, and I think that waste is one of the things we think of, organic waste, as a feedstock in bioenergy, and actually that would be a way of decarbonising that. And then the last thing to mention is chemicals production. You cannot decarbonise carbon-based chemicals. They are made of carbon, but we can, and so when they break down at the end of their life or when they're burnt, they release carbon, but we can try and use renewable carbon from biomass for making those. So that's not energy related, but it's a cheeky extra thing to add in. So then the second thing you asked was about food production and biomass. I think that it's really, this has been a problem in the past, and it's been something that has changed people's opinions a lot over bioenergy. So bioenergy is something that goes in and out of favour a lot, and that makes it very difficult for people in the sector, for investors and things. I think that now the sector is really focusing on non-food crops. So in fact, woody crops like miscanthus and willow and things that you can't eat are actually really good for bioenergy. They tend to have better greenhouse gas balances in terms of in and out. They don't need as many fertilizers and things, and they can often grow on land that food cannot grow on. And if you look at the different benefits that can come from them when you're making decisions, so could they help flood prevention? Could they put more carbon in the soil? If you actually put them in the right place according to all those things, they can give you extra benefits. So I don't think it should be about, we don't want to take all the farmland that we're using for the food we produce and put loads of energy crops there, but we might want to think about where we can put them. Could we put them on contaminated land and use waste and use algae, seaweed? I'm a big fan of seaweed, and all those things, so that we don't have food or energy. We can have both. Sorry, that was a long answer.
Yeah. That's a great answer. Yeah, so that's actually the correct and then the way forward. Yeah, so we are coming up with the time, and my one last question for the brief view on in our own backyard, kind of in our own research area. So before doing a piece of work, so should we also consider the sustainability impact? So what is your view on that? So because we look, for example, I can give you a best example. The dichloro trichloroethane DDT is called. It's a very well-known chemical back in early 90s, used as a insecticide, and also during just after during World War, I guess, used to tackle the malaria disease. And even this Swiss scientist Paul Muller got a Nobel Prize for this discovery. But later on, because of its impact, environmental impact, so it's been banned. So something we should also, before doing some piece of work, so we should need to consider, this sustainability impact. So what is your view on that? So quick view, and we can wind up this session.
I'll just go quickly jump into that, Santosh, just because I'm an experimental researcher and I struggle with this every day when I want to optimize things. Right. And then I'm sort of going through 1 liter of solvent just because my reactor consumes. So I guess what I try to do is use methods like design of experiments, or try to minimize the number of experiments I need to do in order to optimize the working of my reactor, or just be conscious of the fact that, or try and I mean, that's another thing which I'd be really interested in. This is the next step, is to try and recycle the solvent and reuse the solvent as much as possible. But that's something I struggle every day when I'm in the lab. It's not the best thing to deal with.
Yeah, that's really, I mean, I always ask myself this question when I do, because I'm also experimental chemist. So yes, anyone else would like to quick comment on this?
Yeah, I think
yes.
the scope to include this sort of thing as justification statements and considerations whenever we design experiments, put grant procedures together, or start building new projects. If we're designing a system that's going to use something that's very hazardous or dangerous, we have to put a justification why we're not using a safer procedure. Moving into the future, we could sort of incorporate this and say, okay, if we're using something that's very carbon or energy intensive, we have to put a justification to say why we can't use something that's more renewable or less material intensive. And just changing that sort of thought process and incorporating that into the process could be a good way to sort of shift directions towards sort of more environmentally friendly routes.
Yeah, that's great. Yeah, thank you so much for being here today. And with this, this is end of the session. Hopefully, we'll hang around for the next session as well. Thank you so much. Daniel, would you like to say before break anything?
Yeah, sure thing. I'd just like to say thanks to all the speakers, panelists, and please stick around for the next 10 minutes, but please use the time wisely and get a screen break. And we have the future of the sustainable transport coming up next, so it should be really interesting. And thanks again to Santosh for chairing the session. Really appreciate you stepping in for that. So thanks, and we'll see everybody in 10 minutes time.
Hello.
Hopefully everybody is coming back now and has had a good and refreshing break. To those of you who have joined mid-session, thanks for coming along to the Supergen Net Zero Conference. This is the Early Career Researcher Forum. The next session is going to be on the future of sustainable transport. It's being chaired by Hui Liu. And I guess that's all I have to say, so take it away. Thanks very much for coming to chair the session today.
Thank you, Dan. Hello, everyone. Welcome back. Hope you had a refreshing break. So welcome to the second session of today's ECR Forum, the future of sustainable transport. So in this session, we have 3 flash talks, followed by panel discussions of 4 members to discuss the research advances in the sustainable transport. And our panels will give their perspectives on the future direction. So our first speaker is Luis Batsa from Imperial College London, followed by Amruta Josh from University of Birmingham. And then our last speaker of this session, you are all familiar with him. He's our chair from last session, Santosh Kumar from Imperial College London, as well as Diamond Lysos. So just remind you, if you have a question, please post in the chat or remember to unmute yourself to ask during the panel discussion. So without further delaying, so please welcome our first speaker, Luis Batsa. So Luis, whenever you are ready.
Sure, thank you, Hui. Let me share my screen. You can see the screen, right?
Yes, I can see.
Okay. So yeah, thank you again, and thank you to the organizers for the invitation. So I'm Luis Batsa. Sorry. I'm Luis Batsa, and I'm a research associate in electrical engineering at Imperial College London. And today I'll give you a very brief overview of some recent work we have done on trying to understand the value of using electric vehicles to support the grid. And this can be done through the so-called vehicle-to-grid technology. And this is in fact a very simple concept, because it simply means that vehicles could be equipped with bidirectional chargers that could not only draw power from the grid to charge the battery of the vehicle, but also could inject power back to the grid. However, just to let you know that in this work, we consider that the EVs, the electric vehicles, are actually most of the time either charging or simply waiting, not really injecting power that often into the grid. So what I'm going to show here is not really things like peak shaving or energy arbitrage that you might be familiar with, but providing grid support. That means that the EVs provide a service called frequency response. I won't get into too many names today, but this just means that, as I said, most of the time they will be just plugged in, waiting and ready to act if there is any contingency in the system. And as you will see, this is very valuable in grids with a high presence of renewables, which is already the case in the UK. So I think it is key to understand that vehicle-to-grid technology would present a change of paradigm for grid support services. The current state of play consists of a few big generators that provide this grid support, and also a few grid-scale battery storage assets. And what this means is that the system is mostly centralized. So it's fairly easy to predict and to control the availability of each unit. But on the other hand, the cost of procuring these grid support services is sometimes high, and it can increase quite significantly in the future as we keep increasing renewable capacity in the grid, if we don't consider any alternative grid services. So this does open a huge opportunity for new technologies like V2G, vehicle-to-grid, given that this massive deployment of EVs is necessary if we want to meet decarbonization targets. So we could somehow take advantage of the EVs for transportation in a clean way, but also use them to support the wider system. And this also makes a lot of sense because the cost of grid support from EVs could potentially be much lower than for grid scale assets. We basically would buy the EVs, as I said, for transportation. But again, if we can take advantage of this extra benefit, that can be much cheaper than building an asset simply for providing these grid services. But it is also important to understand that EVs present a key challenge because they are inherently uncertain. We cannot know for sure the times when the EVs are actually plugged in and therefore available to provide this grid support through the V2G technology. It is true that we can make some forecasts based on people's typical travel patterns, but we must explicitly consider the potential forecast errors too, because otherwise we would be overestimating the value of vehicle-to-grid technology to provide stability to the grid. As it might happen, then not all the EVs that we expected to be there and be available will actually deliver the support that we need at a given time. So the research question that we have tried to tackle is how can we take advantage of this V2G technology to reduce the cost of grid support, but at the same time accounting for the uncertainty in EVs travel patterns. And we have tackled this question by developing an economic optimization model that explicitly considers the EV uncertainty. So what this model does is it runs the generation scheduling of a power grid while guaranteeing that a sufficient amount of grid support services is available. In this slide, you can see just some results from applying this model to a plausible generation mix in Great Britain by 2030. So here I have summarized just 3 scenarios. One of them is an optimistic case where we completely neglect the EV uncertainty. So this is somehow equivalent to assuming perfect forecasts in travel patterns. On the approach that we have developed, the scenario 2, the green bar, we do account for uncertainty, but we have developed a formulation, a mathematical framework that lets the user, in this case, it would be the system operator, National Grid in the UK, limit the risk of, limit the risk as much as they want. That means that they can limit the risk of under delivery from this vehicle to grid technology. So in the results that I'm showing here, we fixed this risk to 5%, meaning that we can trust the response from the vehicle to grid with a 95% confidence. And the last case is the one with 0 risk, which means that you have to completely neglect V2G capabilities because they do have this uncertainty in travel patterns. So grid support in this case would come solely from supply side sources like gas-fired power plants or grid-scale batteries. And these results show that we could get roughly £1 billion per year savings in cost of grid support services. However, if we are too optimistic, as in the first scenario, V2G wouldn't actually deliver the expected support 60% of the time. But with this method that we have developed, the benefits from V2G are simply slightly lower than in the optimistic case. But on the other hand, we can now fix beforehand the confidence that we want for this V2G support. And this is critical because, again, V2G are very likely to if they are very likely to under-deliver, we would have to resort to more expensive providers of stability support like gas power plants, or in the worst case, we could even have some load shedding. And that's it from me. I mean, the general idea that I hope you get from this flash talk is that we can get benefits from these new technologies that provide flexibility, but we do have to be careful with them because in the case of EVs, we need to model them appropriately, given that their primary purpose is transportation, not grid services, and there is some inherent uncertainty with them. So I'll leave it there.
Thank you, Luis, for the very interesting talk. I would love to hear more of the V2G scenario in the panel discussion. So our next speaker is Dr. Anusha Roche from University of Birmingham. So Anusha, the floor is yours.
Yeah, thank you. Let me share my screen. Hope you can see my screen.
Yes.
Okay, so good morning, everyone. I am Amrita Joshi. I am a research fellow in Energy Systems and Policy Analysis Group at University of Birmingham. And I also work as a local energy system modeling knowledge exchange fellow with ATETA project at University of Birmingham. It is a ERDF project. And with this project, I get a opportunity to work with different small and medium enterprises. So what I'm going to do here is present work which we have done with Nokomoto, which is one of the SMEs through a data project. And what we have tried to consider through this analysis was to find out emissions savings associated with e-bikes. So just to give a quick perspective about bikes in UK transport system, as we know that 1 hour is typical time of on average person travels per day in as per historical data, and until 1940s also there were 1 in 5 commuters were using bicycles. However, with rising car ownership, these numbers has decreased, and you can see in the graph in the middle, which we can see the light blue color pedal cycles, which kind of disappeared over the period of time from 1952 to 2016. So what were the factors which were affecting these mobility choices? So we can consider that it was long-term decisions like career and family size, which is indicated in the outer circle, or those can be further percolated through the medium term choices like where one lives or where one works. And then it comes down to the choice like buying a car and how day-to-day life travel starts. So based on this, we can see that there has been some decrease historically in usage of bikes in particular. However, we can see that in recent years, there has been a good recognition of e-bikes in terms of policy frameworks. So you can see here the hierarchy of sustainable transport, and we can see the active transport in the form of walking or cycling is at the top of that hierarchy, whereas e-bikes also play an important role there. And we can see that the walking and cycling everyone appreciates intuitively that has most social benefits as well as fewest negative effects. It has also been considered that in the sense like globally, and one example is Netherlands, where 40% of riders use e-bikes instead of cars. So through the what we can say the policies which Department for Transport are considering, they have clearly considered that e-bikes are better suited for shorter journeys, and in England almost 24% journeys are under 2 miles, 56% are up to 5 miles. So that means the bikes are having a considerable potential to contribute to sustainable transport. And also there is another aspect related to the cargo bikes, because also the light commercial vehicles also contribute to the transport sector, and we can say that even e-bikes can be used for commercial transport. So if we are considering e-bikes for use in different aspect of transport, then one of the important aspect of them also should be life cycle assessment. And we can see that if we compare them with other vehicles or other modes of transport, like specifically there will be what we can say through the manufacturing or production processes, there will be lesser impact considering the size and material involved in the production. So we what we tried to do in this analysis is to consider the use phase emissions related to e-bikes, and for that what use phase emissions coming from is basically the electricity which is used for charging batteries of e-bike. So for the particular analysis, what we have considered is like different scenarios involving personal or commercial, as I mentioned, for the light duty vehicles, which are like vans, which are used for some kind of deliveries and all. So we consider these two types of scenarios, and where in personal journey there can be we have considered journey limits of 5 miles per day, 10 miles per day, or 20 miles per day. As well as for commercial journeys, we considered the daily journey limits of different things like 20, 30, or 40 miles per day. And what we have considered also is like battery parameters are different for, let's say, personal or commercial e-bikes, because the weight associated with the e-bike and hence the power requirement will be different. So with this particular, what we can say, scenarios, the methodology we try to adopt is like, first we calculated the power required for selected speed of e-bike. So in UK, the legal limit for speed for e-bike is 15.5 miles per hour. Also, we can say that we identified the power assist required, which can be provided within legal limits from the battery, that is 250 watts. And considering these two legal limits, we calculated energy consumption for daily mileage. We evaluated the impact if we the power assist percentage is varied, like we are not going to use the power from battery all the time. There will be some pedaling also, and how it is useful to have a more pedaling we can see in subsequent slide. So then we have done calculations of electricity required for charging these e-bikes, and then using the emission factors data from government's website for electricity, we tried to calculate the emissions associated with that. So in this particular thing, you can see the two scenarios. On left side it is for personal bikes, on right side it is for commercial bikes, and the x-axis what we are doing is varying the percentage of power assist. So that means, like, when in your journey probably you can use 10% of power assist or from the battery, and remaining power is coming from the pedaling of the cycle, and so it can be increasing based on the terrain also. So whether it is a hilly terrain or whether it is in city, according to that power assist can vary. And you can clearly see, which is kind of intuitive as well, that the emissions will be increasing if we increase the power assist coming from the battery. And this is for personal bikes as well as commercial bikes. You can see the numbers, particularly like it is even with the maximum power assist, the emissions associated with electricity are around 100 grams of CO2 for equivalent for daily journey for personal e-bike, and around 200 grams CO2 equivalent for the commercial e-bikes, even when we consider the maximum scenarios. So we can clearly see increasing power assist from battery for e-bike increases the associated emissions. Also, as we know that the power assist is coming based on the battery, and if we are reducing the power assist, we can have more days of autonomy of battery, so that we will need lesser charging, lesser frequent charging of the battery. And we can see that as power assist increases, the number of autonomy days are decreasing. That means you need more frequent charging. So just to compare with other vehicles which are getting substituted by e-bikes, or we are considering e-bikes to substitute those vehicles, we can see the emissions per mile particularly, and we can see the range for commercial e-bike maximum scenario as well as the personal e-bike. The maximum scenario which we consider, it was around 5 grams CO2 equivalent per mile, whereas there is this one of the literature reference where they have done empirical study of like kind of survey analysis, where they have involved different vehicles, and the numbers in the bracket indicate the number of vehicles involved in the study. And you can see the large 2 and 3 wheelers are having 45 grams of CO2 equivalent per mile. Car like 3 or and 4 wheelers are 48.
Sorry to interrupt. I think you have to wrap up.
Yeah, this is my last slide. Yeah.
Okay, great. Thank you.
Yeah. So this is kind of here we can see that e-bikes have much more potential to what we can say reduce the emissions if those modes of transport are replaced by e-bikes. So this is I'm just trying to acknowledge my supervisor and the team, Ateta team, and the Nokomoto SME. And thank you everyone for listening. Yeah.
Okay. Thank you, Amruta. So our next speaker is Dr. Santosh Kumar from Imperial and Diamond Lysos. So Santosh, the floor is yours.
Yes, thank you. Give me a second. I'm going to share my slides. Yes, seems like it's loading.
I think it's not in the full screen.
Oh, it's not in the full screen. Right, it's okay.
No, it looks okay. I actually think it is full screen. It's just a different type of PowerPoint presenting, but it's absolutely fine, Santosh.
Okay.
It's fine. All right, okay. So yeah, so next 5 minutes, 5 or 6 minutes, I will be talking on solar biofuels, via engineering innovation. I'm basically experimental chemist, recently relocated from Imperial to Diamond Lysos. So my research particularly focus on converting, carbon dioxide and also organic waste or biomass platform molecules into hydrogen and other low carbon fuels. So the reason I'm doing this work is the motivation is clear. So one thing is environmental pollution, and the second thing is energy demand. So change in, rise in population and change in lifestyle, so has, greatly increased the consumption of energy. But unfortunately, we still mostly depend on fossil fuel-based resources. I would say after Industrial Revolution, so we started basically polluting, our Mother Earth. So this is, and when it comes to even transport, so we also still, dependent on petroleum and non-renewable feedstock. So this is basically, time to, move to clean future. So for that, we need sustainable routes for renewable energy sources to fulfill our energy demand, and as well as protect our natural environments. So my pathway is artificial photosynthesis. Particularly, I work on artificial photosynthesis. The reason I work on this, if you look at this process, input are very abundant material, such as sunlight and water and carbon dioxide, and you can also use, the biomass or organic waste. And the process is basically very simple. We just need to mimic the nature, what it does to create its own food. So basically, we need to create a kind of material. It should be a sustainable material, so that can copy the nature's photosynthesis, can convert the carbon dioxide or even biomass into useful chemicals and fuels. If you look at the products, some of the products from this process, such as hydrogen, can be directly used as a transport fuel, and other industry like ammonia, fertilizer, ammonia synthesis, or even heating the building, heating up the buildings. So, and other low carbon fuels such as methane and carbon monoxide and methanol are great feedstock for the industry. So, well, if you look at the technology readiness level of so basically solar forward technology readiness level, there is some mature market in solar cells and self-cleaning surfaces, and even indoor air purification and also a bit of water purification. But where we are lacking is hydrogen production and biomass and CO2 conversion. So this is what, in particularly, my research is aiming, in at least next 10 years to, get that stage, prototype or market entry. So within the last 2 years, I have, last couple of years, I would say, we have made some progress. Particularly, when I started doing in solar fuel area, the research in solar fuel area, I achieved for us like 0.2 quantum efficiency. So from there to today, we moved from 0.2 to 1.26 quantum efficiency for hydrogen and other fuels. Particularly with the hybrid material is composed of cesium lead bromide and copper, and also reduced graphene oxide. So, but this is not enough. So this is still early, early stage. Something you need at least 5% to do. Go for scale up. So what I see the future of the solar biofuel technology-based circular economy is so one thing is we need a sustainable material that maximizes the utilization of sunlight. That's the major focus. But not only that, but also we need to probe these materials at atomic level, and also these interfaces
to interrupt. I think you also kind of need to wrap up.
Right. Yeah. So this is the last slide. So you need to look at and to scale up. We need collaborations with industry. That's the way forward. I see. So I've been involved now currently in a multi collaborative project with industry and even 5 European countries involved. So we are looking all this together, designing material and probing this material and scaling up in collaboration with industry. Yeah. Thank you so much for all the project partners.
Okay. Thank you, Santosh. So may I invite all our speakers, also Dr. Yusuf Al-Sangar from University of Birmingham to join the panel discussion. And Santosh, are you there? Okay. Thank you all for your time and for joining the panel discussion. So maybe we start again with you give a brief introduction of who you are and what your research topic is, so people would know better of and also what type of question we should ask. So maybe start with Amruta.
Okay, so as I mentioned, I'm a research fellow in University of Birmingham, and I also work under a data project where we actually give some technical recommendations to small and medium enterprises by understanding their businesses and what they actually, how they can do better in terms of reducing their carbon emissions and improve energy efficiency. I work in energy systems and policy analysis groups, so we also consider policy aspects of energy systems. So my work is considering the policy aspects of energy systems, where energy systems involve renewable energy like solar photovoltaics, energy storage, and so on.
Okay, thank you. Yusuf?
Yes, good morning, everyone. I'm Yusuf Al-Saghir, a research fellow at the Birmingham Center for Fuel Cell and Hydrogen Research, and I've been involved with the ATITA project within the university to support SMEs in Birmingham area and Solihull. And I have research focus on fuel cell system application design and control for stationary and mobility application, as well integrating hydrogen system to renewable energy sources. Thank you.
Thank you. Santosh?
Hi, so I'm Santosh Kumar. I'm currently based in Diamond Light Source. I'm also visiting researchers at Imperial College London. My research mainly focus on converting carbon dioxide and biomass into useful low carbon fuels, particularly using sunlight as the input energy. So I've been working in this field for like more than 5 years now. So particularly designing materials and also probing these material and the electrolyte interface to understand and boost the efficiency. So in order to scale up these processes.
Okay, thank you. Luis?
Yes, hi everyone, I'm Luis Patesa. I'm a research associate in electrical engineering at Imperial College, and my main research focuses on how to achieve a good technical and economic operation of low inertia power systems, which means power systems where we will replace thermal generation like gas fire, coal fire power plants with non-synchronous renewables, basically wind and solar. And also right now I'm the fellow for the World Economic Forum's Global Futures Council on Clean Electrification.
Okay, thank you all. So I see we have a very diverse panelists from different research background as well as from different sectors. So I'm gonna start with one question that kind of relate to you all. So is it more beneficial to take a multi-vector approach when decarbonizing the transport, or we should mainly focusing on the electrification that requires like new infrastructure? So who would like to start?
Yeah, I don't mind. I can start. So I think it's very important to consider the multi-vector sector because in past decades we've been spending on electric vehicles and electrifying the industries. But that's I don't see, at least in my view, I don't see that's sustainable, or we can achieve using that strategy we can achieve our net zero target. So we need to also bring in all other vectors, maybe offshore or solar, and even in hydrogen. I personally feel like hydrogen will be playing a key role in transport industry, and as well as and also as a input energy for many other industries, and also like domestic uses, for example heating up buildings is gonna. But the key thing is as I earlier said, is the source of hydrogen. Is it renewable? Could we achieve in meantime? So that's something the focus needs to be diverted, and also for the transport industry, like linking with the fuel cell research. So that's I feel like but you can't kind of avoid other contribution, like bioenergy or offshore. So these all even small contribution is very valuable in order to achieve our net zero target.
Actually, I do agree with Kumar. I think a multi-vector approach is more beneficial, as I believe to achieve the required level of decarbonizing transport, there is no single approach can achieve that alone. So electrification is one approach, of course, which is important one, but it cannot decarbonize the transport sector because the electricity infrastructure limitations we have. So we need to develop alternatives that can use other infrastructures like gas grid or the current available network of trucks and containers that distribute hydrocarbon fuels, which can be used to distribute hydrogen-based fuels as well.
So I also agree somehow. Definitely we're going to need many different things to achieve net zero, but I think it's also key to understand the urgency of decarbonizing, particularly after the IPCC report came out just last month. It's much more effective to decarbonize really fast now. So say in the next 10 years, decarbonize 80% and then get to net zero by 2050, than to just go on a slow path and then decarbonize quite fast. And I think for most use cases, electrification is key because we have most of the technology more or less ready. There are some challenges, definitely, but cost of renewables has decreased massively. So I think it's maybe different if we are talking about research or deployment. For research, definitely, we have to keep investigating many different things. But for doing actions that we have to take right now, I think the least regret options are mostly on the electricity side.
I must say I also agree with all my fellow panel members that multi-vector approach is important. However, I also think that whichever vector is chosen, it is important to consider the entire life cycle of that technology, right from its components involved for the system in their manufacturing phase, their use phase, as well as end of life phase. So whichever vector or technology we choose for addressing the transport, it will become sustainable only when we consider different life cycle phases and try to minimize the emissions at each of those phases.
Okay, thank you. Yeah, I think it is very important to have the multi-vector and also have to consider the urgency of the timeline, like we have to achieve this decarbonization targets. So actually following what Amruta said, there's a question in the chat from Mikhail about actually, it was addressed to Luis, but I think you all can think of, have you factored in the life cycle analysis of EV battery system having non-cycle life?
So I can start because I think it was related also to the results I showed. No, because what I was showing is the operation of, so 1 year of operation of the whole UK system and how operating costs reduce if we have this support from EVs, right? So the only issue, the only thing that we did consider is we didn't allow the EVs to discharge for this energy arbitrage. So you can think of it as every day when we reach peak demand in the afternoon, evenings, we could use the EVs to potentially put energy back into the grid. But that would cause significantly battery degradation. And since people buy them for transportation, we didn't allow that. So in this case, the EVs would be most of the time simply waiting there. And only when a large contingency, so imagine a large generator comes out of the system, that's when they would actually have to feed energy back into the grid. So it wouldn't be really much different than plugging your EV at night and just leaving it there. It's just doing that in a smart way. We need visibility of those EVs, of course, and we can take advantage of that. So that was the study that we did.
Okay, great. There's also a question from Tom. So with respect to the V2G, would the customers be compensated for the V2G supply, and is this potential cost viability included in the saving calculations?
Yes, good question. So no, it's not included because what we did is understand how the whole system costs reduce. So we only consider, for example, burning gas does have a cost, right? But there is no fuel in the batteries of EVs. So of course, if you are an EV owner, you would like to be remunerated for this. That would be a slightly different story. How can we design a market for these owners? Would there be a availability fee and then a utilization fee in the few cases when we do have to use these EVs? Certainly, we will have to go for some arrangement like that. But we just wanted to understand how many savings we can achieve if we have these EVs. This is an ideal case, of course, when we don't really pay the EV owners for that. If we paid them, well, we would be willing to pay them up to those savings that we see we are achieving from using that support. That's more or less the story.
Okay, I see. Thank you. So yeah, it looks like EV is the most urgent electric solution for the decarbonization. But in terms of the different transportation types, is there a more preferred way of energy for different scenarios? For example, like the vehicles or like ships or the aviations. Do you have any suggestions for different types of energy we should use?
I think we need to somehow motivate ourselves to take the natural way of traveling, like maybe walking and cycling, and public transport is where you can't walk or cycle. So that's key, but the thing is, like, I'm not a expert in economic and policy, but I do understand why do we have so much pride, the public transport. For example, if you want to travel from Birmingham to in Scotland, somewhere in Scotland, Edinburgh, by train, you pay more than what you pay by air, airfare. So these are the things the government has to focus, make more access to the public transport, and where basically we have like, for example, train is, if you compare the train and air, so train is more feasible and less emission. So yeah, and also like buses. So these public transport accessibility has to increase, and kind of government has to bring in collaboration with all other social activists and scientists to bring the awareness in common public, and highlight the importance of not only societal importance also but personal importance, so that would be way forward.
Yeah, taking from what Santosh just said, it is like important to have intervention in terms of, let's say, if we want to incentivize more active transport in the form of walk or cycling, then there needs to be road infrastructure which is suitable for safety of these things. And I must say these are being considered in cycling and walking strategy. We have we have UK government recently published that strategy, as well as a white paper in that direction. Also, I can say that like emissions associated with the air travel, if we want to demote that kind of transport having more emissions associated with that, then there can be something in the form of carbon pricing. So that is another what I can say important aspect which is considered very widely, and will contribute to incentivize the more sustainable ways of transport and reducing the cost burdens on the other modes of transport like electric vehicles or let's say public transport, means buses having electricity as their vector.
Yusuf, do you have something to add on?
Yeah, actually, any new and clean technology would be offered at a higher cost to the public use compared to all non-clean technologies. So one of the solutions to tackle this is to put more restrictions on high pollution technologies, the old ones. So, for example, clean air zone is for instance, is an example. Maybe you don't like it, but it is here. So, this way, people will prefer to use public transport if their current transport mean that doesn't match clean air zone emission regulations. So, our government and maybe councils as well may offer as well subsidies to public transport to reduce their tariffs and incentivize people to use the public transport. Yeah.
So if I can just briefly add to that, yeah, I agree with everything that has been said. I think it's also very important to be really careful with these new policies because particularly in transport, having a fair transition is very important. We saw the Gilets Jaunes movement in France just a couple of years ago, where if we start taxing or putting things like carbon pricing, which is probably the way to go, it's to make these options less attractive. But on the other hand, it can put quite a big burden on people who cannot really afford it, right? And it can cause social unrest and so on. So I think it's tricky, particularly in transport. How do we achieve this? But it's certainly important. I'm myself no expert in policy, and that's why it's probably quite necessary that we, as engineers or scientists, try to engage also with social scientists to understand both the evidence and the scientific approaches with something that sometimes we ignore, which is how can this be actually put into practice, right?
Yeah, that's true. So yeah, in terms of this making public transport more viable for people and more preferred for people to travel, what are the business models for making this more preferred for people? For example, like at the moment, traveling by car for at least 2 people is more cheaper than you taking the train. So is there any business model in place, or if there is, like what's the content or direction should it be?
I can say there have been some efforts in providing mobility as a service rather than in the sense it is more of on shared, means considering individual mode of transport instead of considering individual modes of transport. The entire journey has been provided as a service. That is one of the, what we can say, the models which have been considered, like from source to destination, whatever modes of transport are there, those are considered together and then paid together, means user has accessibility to those in less expensive ways. That is one of the, I can say, models which have been considered in policies.
Okay, that's good to hear. So I saw there's one point also made from Tom about aviation. So there are some projects currently developing the sustainable aviation fuels through the ethanol to jet fuel routes. So I guess in terms of aviation, it's actually quite hard to abate the carbon. So another kind of hydrogen is another source is hydrogen, which people also think it's a way to decarbonize the transportation. So it's probably more related to Yusuf and Santosh. It's what are the ideal vectors for hydrogen, and what are the potential risks of utilizing them, and how can we mitigate those risks?
Yeah, actually, we could find in literature many hydrogen carrier or vectors has been considered for research. And hydrogen vector could be in form of compressed gas or liquid hydrogen, or even chemical as ammonia or any liquid organic hydrogen carrier, or maybe even as a solid borohydride. All these are hydrogen vectors and carriers. So the ideal hydrogen carrier is the one who has the highest volumetric energy density and as well gravitational energy density. So this is in order to be compatible with the weight and space limitations in transport application in general. So it should have the lowest energy as well. It should have the lowest energy losses during conversion from hydrogen gas to the carrier form and then back to the gas form again, unless we develop a technology that uses the carrier as a fuel directly on board vehicles. That will be a different story. Yeah.
Yeah. So to add, Yusuf, I think I see hydrogen as the major contribution to in order to achieve the net zero target in future, but there are 3-4 things to look at. The first thing is right now the way we produce hydrogen is not sustainable, but the thing is we are hoping like in meantime, because if you look at the today's research activities, so there is breakthroughs every day and now. So keeping that in mind, so I fully go with the government strategy with the hydrogen economy. But in the meantime, the research, also the fundamental research, has to be has to be done in order to for example, particularly the renewable way of producing hydrogen, electrolysis, or maybe in a hybrid system like solar and electrolysis to achieve that renewable hydrogen. And the second thing is in centralized hydrogen transportation, the supply chain particularly is the carrier, the hydrogen carrier. So ammonia is looked at one of the potential hydrogen carrier and storage. So the another thing is the safety side.
Yes.
So that's something it's not fully understood. So that's has to be well understood before we centralize and widespread use of hydrogen. Otherwise, we'll be seeing some consequences out of that.
Okay.
Yeah, I agree with Santosh about the aspect of the safety when handling the hydrogen carriers. Since we have handling and transporting and the toxicity of the hydrogen carrier. So I would say there's no one carrier that can offer all these targeted properties, which is safe and high volumetric and gravitational energy density. So we have to compromise and select the form of hydrogen vector that serve well in a specific application. So for example, for passenger vehicles, we have space limitation is a very important aspect to consider. But while for shipping and for our heavy good transport like trucks and buses, volumes are less restricted. So we can use maybe different alternatives. And of course, if we aim to do a strategical decision on best to select what the hydrogen carrier that dominate the economy, then safety is a very important aspect to consider at strategic level.
Okay, thank you all. Thank you all the panelists and also questions raised. I see there are many more pricing questions in the chat. So if you have time, do look at them and try to address, or the audience can get in touch with our panels to have more discussion. So thank you all, and this should be our second break, and at 11 sharp there would be the third session of the ECR Forum. So thank you.
Thank you.
Thank you.
Thank you.
So I hope everyone used that break wisely and took a break from the screen. I know I did. I went outside and realized how cold it was for the start of September. So I'd like to introduce Robin Priest, who is going to be the chair of this final session, which is on securing the global transition to clean energy. We have a number of speakers who I can see appearing on screen and are ready to present. So I'll hand over to Robin. Thank you very much.
Thanks very much, Dan. Hopefully you can all hear me. I assume so. So I'm Robin Priest from the University of Manchester. I'm part of the Supergen Energy Networks Hub. And we've got in this session, I think we've got 5 different talkers who are going to do their little flash talks and outline their topics. And then after that, we're going to have a panel discussion where we'll also be joined by Wei He from the University of Warwick. So I think considering we've got so many talks to get through, best to dive straight into it. So we'll be starting with Gregory from Imperial College London. So I think you should be able to share your screen and do your presentation. So over to you.
Fantastic, thank you. There we go. So hi there, I'm Dr. Gregory Gori from Imperial College London, working with Titirici Group, talking about sustainable carbon materials for next generation energy storage. So I'm part of a team called Titirici Group with 40 researchers working on cutting edge energy storage materials. I'm in charge of technology transfer and commercialization, 7 years in industry, as well as 6 patents under my name. And I work for Professor Magda Titirici, who is a chair of sustainable energy research at Imperial and co-inventor of a process known as hydrothermal carbonization. So our motivation is to bridge the gap between material supply and renewable energy itself. This reduces the energy consumption, trying to replace scarce materials with more abundant eco-friendly ones, reducing CO2 emissions and energy intensive use, upcycling and recycling waste, overcoming fossil fuel dependence, and creating these carbon-based materials which are inherently important in all energy storage devices or secondary batteries that are around at the moment. So what we do is we produce low-cost, eco-friendly materials from biomass waste. It's a very environmentally friendly process, and we also take a lot of inspiration from nature and biomimicry in order to engineer the microstructure of our carbons. At the moment, one of the main problems is that lithium-ion batteries use critical supplies of lithium, which are endangered, as well as other harmful materials such as graphite and cobalt. You know, cobalt, we know the problems are actually mined by children in the Congo in very terrible conditions. And there's not really any recycling demand that's good enough for the problem that we face. It's very much in its infancy. And one of the solutions here is we can use sodium-ion batteries, which are the next generation kind of battery that's being developed right now. Sodium is 40% the price of lithium, and easier to transfer and much, much safer. Now, in more looking into the future, there's other concepts that can further revolutionize the way energy storage is used and make it eco-friendly. One is this idea of a transient sodium-ion cell, where we can use stable materials to create a sodium-ion battery pack. And after life, this will be decomposed by the environment, so we can just throw it away in nature and it will become benign, non-toxic products. And this is kind of a more systems-wide approach of looking at the whole ecology. And we can try and imagine a world where our electronics are actually essentially part of the ecosystem instead of a problem for it. We work with many collaborators around the industry and are trying to get this stuff out into the real world right now. And we'd be very interested in hearing from more people and anyone who'd be interested in our technology. And our vision in the future is to replace non-renewable carbon materials with sustainable carbons and enable a big paradigm shift into eco-friendly and eco-regenerative energy storage. Thank you very much.
Perfect. That was lovely and efficient and very clear, and I guess kind of really highlights the kind of challenge around needing this technology to help us rapidly decarbonize, but then also that technology itself also has carbon costs associated with it as well, and so needing to decarbonize those technologies. And I think that's probably something that we're going to touch on more maybe in the panel discussion, looking at how this works on a global scale. So thank you very much. Next up, we've got Stuart from the University of Exeter. So over to you.
Okay, thank you. Make that big. Okay, morning everybody. Yes, as you said, I'm from the University of Exeter, so I'm talking about the transition to clean energy, particularly talking about marine renewable energy and tidal stream energy, which is what we're working on here. Talking about the TIGER, the Tidal Stream Industry Energizer project, which is a academic and industrial kind of collaboration, big collaborative project working on tidal energy, trying to sort of basically reduce the cost of tidal energy. So tidal energy has lots of great advantages, predictability, for example, lack of visual interference and so on. But currently it's very expensive. So levelized cost of energy, currently we're around £300 a megawatt hour. And you can see some other options there that are significantly lower cost. So what we're trying to do is reduce so that people like the Chancellor are willing to give us a bit more support. So we can talk about two ways that we do that. So this is a graph from the Offshore Renewable Energy Catapult a while ago, looking at how we can get from the current cost down to some lower costs by the time we get to 1 gigawatt of installed capacity. So the areas that we are working on, particularly here at Exeter, work on reliability particularly, which influences this kind of learning by doing sort of area. And also we're working on some material efficiency, some life cycle assessment type work as well, which helps sort of reduce investor reluctance, gives a bit more confidence, and can therefore help reduce this kind of cost of capital. So that's how those steps that we're contributing to. So first of all, I will talk a bit about the reliability stuff. So this is some work we've just finished recently, myself and Professor Philip Tees. So we've been working on, we looked at all, as far as we know, all, there may be one or two more, but most of the major ones, the tidal stream energy deployments that have taken place basically since the very first one off the coast of Devon in 2003, all around the world between then and last August. And we looked at whether they succeeded or failed, various kind of degrees of failure from spectacular failures to sort of just curtailments when they were removed before they failed, to underperformance, to things that just didn't generate the power they were supposed to. You can see that the majority was successful, but going forward, there's definitely work we can do there on those, particularly on those red ones, and see how we can improve efficiency and reduce cost by reducing operation and maintenance costs. So we found a link actually between, I'll kind of just run through this, is quite hard to explain quickly, but so we looked at all the deployments over time, and the main link that we found no real correlation between sort of type of device or type of foundation or various other aspects that we looked at, but there was quite a strong correlation between the site conditions they were installed at and the failure or success of the device. So you can see here the years that have grey bars indicate that there were a lot of deployments in high flow rate sites, so sites with really high speed flowing water, which makes sense because that's got most energy in it. So those are the ones highlighted in red. If we swap them over to a percentage, so that's now looking at the percentage of deployments that were in high flow rate sites. And if we overlay onto that the failure rate, you can see basically that's actually, sorry, the success rate. So going downwards is increasing number of failures on that line. You can see that basically as the more devices were deployed at high flow rate sites, more and more of them failed. Kind of makes sense. But then we kind of looked in a bit more detail into this, and we've got a paper that if you want to read a bit more about this, but we found that there are these sort of 4 phases of the sector. This kind of development phase when everything was heavily monitored and we made sure that absolutely everything was working perfectly. Therefore, there weren't many failures. We then expanded, knew we needed to reduce costs, so that monitoring things was reduced slightly. But we also wanted to extract more energy, so we went to higher flow rate sites. Things started to go a bit wrong, a bit more failure. But then you get into this yellow phase where we start to do some learning. So we went back away from those high flow rate sites a little bit and started to kind of see, right, what went wrong? How can we improve this? And then you start to see that success rate increasing again, and then just towards the end we get into this kind of green area where you can see deployments at more high flow rate sites, but this time coupled with a higher success rate. So we're not getting those failures because we've done the learning that we can see in that kind of yellow phase there. As I say, lots more in the paper. That's a very brief summary. Okay, next bit, we've been looking at how we can improve levelized cost of energy by improving confidence a bit. So sort of just demonstrating the green credentials in ways other than just carbon footprint and footprint of energy for this. So we've been looking at a life cycle assessment study. It's been mentioned a few times already, which is always brilliant. It's one of my favourite things. So if I just look at a bit more detail at this, again, there's a whole load of information appearing in front of you in about 20 seconds to talk about it. But what we're looking at here is the relative environmental impact of a turbine blade made of different things and disposed of in different ways. So along the bottom, you can see we've got steel options, we've got glass fiber polymers with various end-of-life treatment, carbon fiber polymers, again, with various end-of-life treatments, and some more innovative recyclable epoxy and bio-based flax products. You can see various things. You can see that the bio-based products and the composting at end of life turn out well. Carbon fiber has quite significant impacts, particularly at the end of life. Again, paper coming to talk about this. So just to close, part of Tiger, we're also doing some testing on these bio-based products. So we're not saying, you need to switch to these innovative products that you never heard of. We're saying we've done the life cycle assessment, and we've also tested these things. This is going on at the University of Le Havre. Tested these things under the water, and they perform comparably. This is how you can reduce cost of energy. And finally, we're putting it into a friendly web-based tool that will let the developers see the work themselves. So yeah, if you want to know more, go to the Interreg Tiger website. There's a European Wave and Tidal Energy Conference coming up. Don't know if anybody's going to that. If you are, I'm talking about all this stuff there, or we have papers about various things in renewable energy and in applied energy coming soon. Or get in touch with me if you'd like to know any more. Thank you very much, and apologies for being a few seconds over.
No, don't worry at all. That's really interesting. Always interesting to learn a little bit more about tidal as well. I guess I've always been a little bit surprised that, considering, like, particularly in the UK context, with the amount of coast that we have, that maybe we haven't developed tidal a little bit further. So really interesting. Thank you very much. Next up, we have Anurag from also University of Exeter as well. So over to you and your presentation. Oh, you're muted at the moment. There you go.
Yeah. Good morning, everyone. Thanks, Robin, for the introduction. I'm just going to share my screen. Hope it is visible to all of you.
Yeah, we can see that. Just make it full screen now.
Yeah.
Perfect.
Perfect. Okay, thank you for the invitation, and wonderful to be part of this clean energy ECR forum. So hello everyone, I'm Dr. Anurag Roy, working as a postdoctoral researcher in the Solar Energy Research Group, University of Exeter, Cornwall campus in UK. We are mostly everybody's talking about how we can secure our clean energy system for the future. So being as a material chemist, my focus is basically deeply on the materials perspective. So which material will be benefited for clean energy production? That's what I'm doing in my research. So before moving a little bit of my research details, we have to understand what are the 7 key principles of the security to gaining this clean energy transitions. So if you can see, I'm not going to read out, there is no meaning to that, but the thing is we have to keep in mind these 7 points, and all the 7 points need to be clean and need to be satisfied with our research. So that is why the clean energy transition is actually going to portray. So I'm working on the solar energy system. As you can see, solar is free and there is unlimited and we don't need to pay anything to get that energy. It is naturally available. So to gain the solar energy in a multiple various form, there is a multiple application of solar light utilization through maybe a photovoltaic system, through photocatalysis system, or through electrocatalysis system. And of course, there is another part is building integration purpose. So all these things are related to the solar energy things to make it a clean energy production. And that is my core research of interest. So as I say, my current research activities are associated with the three major junctions, which calls a passive cooling, third generation photovoltaic, which is not silicon related, and of course our wastewater treatment. So currently, being a postdoctoral researcher, I'm basically focused on passive cooling and the third generation photovoltaics part and their integration, that how we can use this two method together to make it a translational research. So we synthesize different material, different chemicals, using different chemicals to get various morphology or various materials that can be utilized to entrap the sunlight and can be useful for various solar related applications. So maybe it is a passive cooling where we are trying to replace the air conditions with our natural coating system. And also we use some concentrated solar light concept where the light entrapment can be, giving more efficiency for a very smaller size of cell, and it will reduce also the maintenance cost. As well as there is a solution process solar cells fabrication, which is called the third generation photovoltaic, where we are replacing silicon with some very more abundant and very easily available material, and that can show a very high benefit of efficiency improvement. And a bit of my research is also focusing on the wastewater treatment and how we treat the wastewater using the sunlight. That is also an interesting part of that research work. So through various photocatalysis and the electrocatalysis method, we are degrading the water, especially the metal ion recovery. So the basic, the very fundamental science of what we need to understand through this, that the light entrapment strategy, because solar having a broad range of sunlight starting from its UV, ultraviolet to the NIR part, so far IR part, but unfortunately the scientists still not entrap the whole sunlight region. So we have to think that there is a plenty of light, it is free of cost, it is unlimited, then how we can entrap the whole set of sunlight at a time using the material. So there is something, the material strategy we need to develop. Through that we can entrap the material and generate more current and more efficiency. So these are few schemes you can see which I have make to design that how the light entrapment will be benefited, using some metal oxide development or some morphology production. Maybe it's a 1D structure, it's a 2D structure, and mixture of some heterogeneous structure, how the light can be passing through interfaces of that material. That is also an interesting point of research of my current work. And with this, of course, there is a focus of the renewable energy production, which has been, meet a goal to start in the Paris Agreement as well. So we need to set a goal map that through the energy transition roadmap followed by the energy economy environment model and their socio-economic footprint. So being a solar energy guy, I need to focus the sunlight and solar thermal part, that because beside of light, there is another property of light is heat. So how we control both light and heat using various material aspect, that is a challenging factor, and we need to produce a clean energy in terms of that in keep in sense. So yes, as I mentioned, that sustainable future is belongs to the solar light. So we have to think how we utilize the solar light as many as we can. And of course, there is a huge socio-economic footprint that can be reduced. The carbon emission can be reduced if we utilize the solar energy in a proper way. And we have to think about a proper material selection and its swift transformation. And with this, we need to select, there is natural elements are available, but we have to choose that which element, which material can be benefited for more and more solar energy conversion. So yeah, that's it. Thank you.
Thanks very much. Really interesting. I mean, personally, it only took about a week of slightly hotter weather for me to get very interesting in passive cooling. So I'd be very, very interested to learn more about that and what I need to coat my house in to try and bring it to a more bearable temperature. Thank you very much. Next up, we've got Matthias from, where are we going? Sorry, from Imperial College London. Yeah, perfect. So over to you for your presentation.
Thanks. Can you see these slides well?
Yep, that's perfect.
Thank you. So hello everyone, I'm Matthias Dovolti from Imperial College, working in the Eslava group with Salvador Eslava. And I'm going to talk about solar water splitting a bit because that's what I'm working on. But first, just as motivation, we are here all to talk about climate change, and that's obviously one of the main reasons why we need to deal with renewable energy. But for me, working in this area is also great because I know that with cheap energy, not just with renewable, but we also need to go with green energy. We can enable people to work their way out of poverty. They can get better to, they can get access to better education, can improve their health and well-being. So that's another part of the motivation for me, why I really like working on this area. And of course, yes, the energy demand in the world is growing and it is expected to grow a lot. And if we want the world and the developing countries to have an improved quality of life, this will just continue growing. So we can't really stop that. So the solution really is to go and have this transition towards renewable energy resources. I really like this map. I've been working during my PhD on solar cells, perovskite solar cells, and these small areas on this world map shows that if you covered these areas with 20% efficiency solar cells, basically you could get all the energy you need for the whole world. So there's an abundance of energy coming from the sun. So if you could use this, then all the problems would be solved. One of the new emerging materials for solar cells is perovskite, which has been increasing their efficiency from 2009 from 3 to 4% to 25% or 26% today almost. So perovskites are a certain crystal structure. It's organic, inorganic, or there are all inorganic versions of it, but they are very great because they can absorb loads of light. They are very efficient in separating these charge carriers. And you can print them large area, so you can solution process them, which can drive down the price of fabrication as well. So there are loads of challenges with perovskite solar cells, and I've been working on this, trying to understand some of the losses in perovskite solar cells. So that's one way we can go towards. And of course, this work of trying to understand non-relative recombination losses and try to avoid them in solar cells is one way to improve their efficiency. There's always the stability question. But altogether, this technology seems to be improved enough that, for example, Oxford Photovoltaics is already trying to commercialize it on top of silicon solar cells as tandem devices. So the question is, what else do we need than solar cells where we could use perovskites, which seems to be a very disruptive new material and technology. And the challenge with solar cells is why that cannot give the solution just in itself is the intermittency of solar power generation. So we need to store all the energy we generated, and you know, batteries could be a possible solution for that, but we have seen in previous presentations that there are questions and problems there with the shortage of lithium or cobalt, for example. So another way could be solar fuels. So with water splitting, using the energy of the sun, we could split water into hydrogen, and then with this hydrogen, which would be a green hydrogen, we could store energy for longer term, and also hydrogen, very importantly, could help to decarbonize other sectors which are hard to electrify. So with this motivation, currently I'm working more on water splitting, and just to show that in the UK's roadmap, if we see this scenario for 2050, I believe this huge green area compared to today's energy use is coming from hydrogen. And on the right-hand side, you can also see that the hydrogen demand is expected to increase up to 20 to 30 or 1/3 of the whole energy needed to power the United Kingdom in this case. we talked about this a little bit, and I think it's a very important part that in the plan at the moment, almost all of this hydrogen is planned to be generated by the cheapest form, which makes sense, of hydrogen generation, which is steam methane reforming. But this is blue hydrogen. It has it's not sustainable source, and it's a carbon intensive process. So it would be ideal to, on the long term, to generate all of this hydrogen from green energy, so renewable energy. But at the moment, the price of these technologies, if you look into some techno-economic analysis, is much higher, 4 or 5 times higher. So basically, the challenge is to drive this price down. This is what I believe will help on the long term, so that we can turn all of this blue hydrogen to green hydrogen. And this is what photoelectrochemical water splitting could help with. So water splitting is a process where you have two semiconductor layers and you absorb the light, and at the interface with an electrolyte, you drive the splitting of water into hydrogen and oxygen, which is called artificial photosynthesis many times. But very importantly, from the energy of the sun, you get hydrogen, and you can use that as a solar fuel. Yes, you could use solar energy and electrolyzers, but and that has potential very much. But having all of this in one system, being able to have it off grid, just generate hydrogen right away from the solar cell, gives a huge potential for photochemical water splitting. Here are the key challenges which we as researchers are trying to solve to drive down the price to this target of $1 to $2 per kilogram. So very importantly, we need to increase the conversion efficiency. We are not there yet. We need to achieve much longer stability, and we need to do all of this from materials which are earth abundant and they can be fabricated with cheap manufacturing, such as rotary solution processing. And I talked about perovskites and solar cells because if we take that, that would satisfy many of these requirements. So just in a final slide to show that my current research, or in our research group, this is a previous research, you could take perovskites and use them in photoelectrodes, use them in water splitting, and in this Nature Communication paper, we have demonstrated from our group that you could use all inorganic perovskites and put a protective layer on top so that you can put it into water and generate electrolysis. And my current research is focused on increasing the efficiency and stability of such perovskite-based photoelectrode systems, for which we need to understand loss mechanisms, improve selectivity of the layers during band gaps, and you can apply more than just one layer to absorb the whole range of the sunlight. So this is what we are hoping to contribute with towards the green hydrogen generation. So with this, I'd like to thank you for your attention and looking forward to the panel discussion later.
Thanks very much, Matthias. I think a great introduction to another side of the kind of how all these renewables can be used to fill out the full kind of energy landscape that's required here on this transition. So very useful. Thanks very much. And over to our last presentation, which is going to come from Simon from Pyrogenesis. So over to you.
Okay, can you see me?
Yeah, I can see you. Can't see your presentation yet.
Right, I just share my screen. Okay. Right, can you see my screen?
Yes, we can. Perfect.
Okay, so I was asked to, talk about securing a global transition to clean energy. So my name's Simon Igofossi. I'm the co-founder and CEO of Biogenesis. We're a bioenergy, biofuels technology provider. And I led the implementation of 4 projects across Africa funded by Innovate UK. So I'm going to share with you some of my perspectives today on energy access on the continent. One of the key capabilities that we recognized that we had to develop in order to deliver this was geospatial analysis. And that is essential to enable us to locate settlements and their proximity to the biomass that we use in our technology. More importantly, it enables us to understand population density, energy use and affordability when we combine that with the field work that we carried out. So as you can see on the image on the right, this was a village that we digitized the buildings, and then we sent people in on the ground to survey those buildings and energy use and affordability. That gave us really important information. So the key findings of that was that household electricity spend can vary from as little as £3.80 a year to £460 a year. Now, what that means is that the way that you distribute that electricity, you've got to think about. And we found that battery distribution is preferable to mini grids in many locations. The other key thing, of course, is that looking at the availability of biomass. So we developed harvest date detection and area detection. So that enabled us to, using satellite data, quantify the waste biomass that was available at any location. And we found that many villages produce sufficient waste biomass to meet their energy demand. Also, when that biomass was going to be available was another key finding for us at different locations. All of this helps to, decide whether we've got a commercially viable business case for our technology at a particular location. So this is what waste biomass looks like from after the harvest. You've got people who will gather it up, hopefully, and then deposit it somewhere, but typically it has no commercial use or value, and it's a source of greenhouse gas emissions as it decomposes, and sometimes it's just burnt indiscriminately as well. So how do we solve all of these problems for these remote communities? Well, we decided we would develop a system which we called pyrochemy, and we wanted to ensure that it needed to be feedstock flexible. As you can see, the different use cases mean that it also has to be application flexible. So at any one point in time, you might need electricity, but only so much. At other points in time, you might need process heat. But if you want, you've not got very much use for any of those things, then you might want to upgrade the value of your waste into a commodity. And so working with Aston University and the Ebury team, they've developed a method for converting the bio-oil that our technology can produce into a renewable kerosene. So we are using the waste that comes off the fields, and converting it into these useful products for these communities. Now, there's no point us doing all of this without the people on the ground not knowing anything about it. So we also developed a social media capability in the countries where we operate. So since January, that social media capability has given us over 500,000 views, the most coming from Nigeria, second largest, of course, in Ethiopia, and then we also operated in Sierra Leone and Liberia. And this means that we're now receiving regular inquiries from people, in those countries. I'm actually talking to you at the moment from Ibadan in Nigeria, and, conducting regular visits to prospective customers and stakeholders and communities that we want to work with. Our social media presence in Africa, it seems that Facebook has done us very proud, and followed up by Instagram. And, so regularly we're achieving, over 100,000 views per month. I think we've exceeded 160,000 views this month in total. So these are great platforms for reaching our audience in Africa, across Africa. This gives you a look at, how that audience turns out in terms of gender, and there is a slight imbalance there. So women are representing, only 23%, and this seems to feed into this statistic, which in Nigeria, women account for 20% of engineers. So one of the things in that operating our machinery in the field, we've had to develop a recruitment strategy that's inclusive, because we don't want women to lose out on these skilled roles that we're going to be creating with each of these installations. And we've also, learned from our research in the field that we need to use stuff like, neutral coded language in our job descriptions, so that we can recruit, train and retain, more women in the workforce, especially in technical roles. These are the kind of devices that are being used. So typically mobile devices are preference. So, 2/3 to 1/3 PCs, and that's essential. It feeds into the recharging market as well. And then age ranges, it seems to be a difference between East Africa and West Africa. So 26 to 34 was the largest age group in East Africa. And in West Africa, it was a 36 to 44-year-old age group. So all of these things are starting to tell us a little bit more about the dynamics of our target audiences that we want to work with and the people who are going to be impacted by the installations that we're going to be bringing to these communities to create energy access. And I'd just like to say thank you very much to all of our sponsors and our partners, and to Supergen and to your audience today for listening to us. If you want to get in touch to speak about potential collaborations in and across Sub-Saharan Africa, I'd be very happy to speak with you. As I say, I'm on the ground at the moment. Thank you.
Brilliant. Thank you very much. I think a really interesting perspective also on the kind of both from the flexibility of the device in terms of it not just being it produces electricity, but it produces that whole suite of various things that could be useful to different communities, and then also on the kind of those routes into kind of commercialization and engaging with those stakeholders on the ground. So thank you very much. That's all of our talk, so we're going to move into the panel. So if I could invite everybody on the panel to turn on your cameras and join the conversation. We should also be joined, I believe, by Wei He from the University of Warwick. Brilliant. I can see you've joined as well. Fantastic. So we'll do the same thing that the others have done. So start, if you'd like to go around and introduce yourselves just very, very quickly, and we'll go in the order of the talk. So I'll let you go. So Gregory first.
Yeah, I'm Gregory Gregori, and as I said, I work for Titirici Group at Imperial College London, looking at the conversion of biomass into useful carbon materials for energy storage applications.
And Stuart?
So yeah, I'm Stuart Walker. I work at the University of Exeter down in Cornwall on the Interreg Tiger project, so looking at tidal energy from reliability, life cycle assessment, and sort of overall environmental impact point of view.
Thanks very much. Anurag?
Yeah. Hi, everyone. I'm Anurag Roy. I'm working as a postdoctoral researcher at University of Exeter Cornwall campus. I mostly work on the solar cell integration and coating development for a glazing system. So currently I'm working on that.
Thank you very much. Matthias?
Hello everyone, I'm Matthias T. I finished my PhD at Imperial College. I was working there on perovskite solar cells and understanding the losses in them. And then what might be relevant, that for 3 months I've worked for a short time for the Sustainable Energy Journal Joule as a scientific editor for a while. So that was very interesting. And then now I'm again back at Imperial College doing research as a postdoc research associate on photoelectrochemical water splitting.
Brilliant, thank you. And Simon?
Hi, I'm Simon Igofossi. I'm the co-founder and CEO of Pyrogenesis and co-inventor of our containerized waste-to-energy technology called Pyrochemy.
Brilliant, thanks very much. And Wei?
Hello everyone, I'm Wei He. Currently I'm a Real-Time Engineering Research Fellow in the University of Warwick. So my research mainly focuses on energy storage, mainly like large-scale energy storage and heat decarbonization and water desalination.
Brilliant, thank you very much. So I'd like to just encourage everybody as well to put any questions they might have for the panel into the chat. There have been a couple of questions, but I think Stuart might have covered those off. They seemed quite specific and technical. What we do have is some other questions that that we'll dive into first while you guys are typing yours. The first one I'd like to ask is, how do we ensure that decisions being made around net zero appropriate for, I mean, the question's phrased here as the majority of the population, but really for all of the population, including those with very limited access to resources. And obviously we're talking about this as a kind of from a global perspective. So there's going to be very different possibilities in different countries and in different nations in terms of how they're able to act towards a kind of a global transition. So what are some of your opinions on that? I don't know if anybody would like to open things up there.
I could say about some of the work that we've been looking into about carbon credits. So at the moment, if you're looking at sub-Saharan Africa and the amount of investment that's going into carbon credits, it's very low in comparison to the West. And there's a lot of things that industries or communities could do that would, with that type of investment, could achieve a lot of either carbon offsetting or carbon removal. So I think making sure that there are mechanisms, that are developed and resourced to, finance projects that will deliver, carbon removal, especially rather than offsetting, then that would be something that could, is very much needed and would be able to stimulate a lot of growth to achieve that.
Yeah, I could add on something. So I think it's more about, it's not only about limited access to resources, more about how to optimize the local resources available. It's more about depending on where you are, you may have different infrastructure, you may have different energy needs. So it's more about, to align with the local community, to solve their needs using the resources available, and also probably bring the expertise from the external community. Or one example, in my project I worked on is more about to solve a water issue in India using renewable energy, mainly solar energy. So more about we want to work with the local company, to use a local supply chain which can manufacture a system at a low cost, and bring the technique which probably has been demonstrated in other countries, which be feasible, and with all the local labor and local the manufacturing capability, we managed to build one system and then transfer technology to a local company, which they can scale up the system. So that's particularly something I think will be interesting, to solve the issue in some area which may have limited access to resources.
Thank you. Any other opinion?
I'm just going to agree about the kind of the localization is or sort of taking advantage of what's there locally. So partly in terms of resource, and obviously, our tidal technology is there's a whole big chunk of the world that it's not suitable for because it's nowhere near the sea. But there are certain very specific areas, like there's sort of island communities that are currently powered by big banks of diesel generators, where for those small island grids we can really make a difference. And things like as well, not sort of using the local resource in those terms, but also in terms of things like, for a resource assessment and things like that, we can send in really expensive, monitoring vessels, and we can spend loads of money and make the energy really expensive because of all the upfront work that we have to do. Or if we engage locally and speak to fishermen and speak to the people who've worked in those areas for years, then you actually don't need to do all those expensive surveys. They pretty much know all the answers anyway. So there's a lot of kind of, the local resource in terms of the actual resource that you're going to get the energy from, but maybe also in terms of the, I don't know what you call it, a human resource or something like that, and sort of thinking maybe a bit locally, I would say is an advantage. But sorry, Matthias, I think I spoke over you.
Oh yeah, no, that's great, thanks. No, I was just thinking about the cost, and I think that's just very important to drive down the cost, and I think developed countries can take leads and putting into the energy, into research and development, and getting the technology to a certain stage when, I think solar cells are a very good example, when the levelized cost of energy is now so very low. I think in two-thirds of the world, it's the lowest or cheapest type of energy, and that could be a big help towards all the other countries where all the knowledge could be transferred. So I see that as a way of helping less developed countries as well. And on that note, I don't know if I've missed that, but could I ask you, Simon, about your technology? How does it compare in terms of cost to other technologies you are competing with?
So far, it seems very good. So we can compete against solar. We can typically, do very well, especially against diesel genset prices. And the reason being is that we have multiple income streams to facilitate that. So we're not just reliant on electricity sales. We produce, low carbon heat, process heat, so that, we can generate income from that. The biochar that we produce as well, we can generate income from that, the bio oil. So we switch our production to suit both the commercial business case and also the demand. And hence why we discovered that actually using rental batteries as a way of distributing electricity, rather than investing $150,000 to put in a mini grid where people are only spending, you know, £4 a year on electricity, you know, so a village of 2,000, it'd take you 20 years to pay off that investment, you know. So there's these ways that we can switch around, and that's what is essential. You have to have a technology that's very flexible in its application, and then also you've got to find out ways that the business model will still stack up depending on what the use case is and what they've got, because they've got an abundance of waste biomass which could be converted into high-value commodities. So that's where we found a sweet spot for the application of our technology.
So there was a question, Simon, as well, just somebody asking, is there any, a question from Scott in the comments, are there any differences in energy demand between the kind of East and West African countries? And also what was the main reason for such a range in energy usage that you saw? So you see from £4 to £400 per year.
Yeah. So the £4 case we saw in Ethiopia, and the £400 is in like Nigeria. And the key determinant is population density. So in Ethiopia, the way that the rural communities are, they're very spread out. So they'll be spread out, you know, the houses will be, you know, and the villages will be quite dispersed. The people are, you know, they have more space between themselves. Whereas in Nigeria, they all like to seem, you know, they literally live on top of each other sometimes. So population density, and that's a cultural thing, a historical thing, that's just how their communities have evolved. So, and also, you know, I mean, there's a saying that throw a stone, you'll hit a Nigerian. Okay, what that means is that there's a lot of Nigerians that are very well traveled. There's a lot of Nigerians in the diaspora. Nigeria is the most populous black nation in the world. So there's a lot of people who are sending home money from abroad. And therefore, you know, the people who are living in rural locations, they all have mobile phones. They'll, you know, they've got satellite TVs. So they are energy consumers. It's not difficult for them to suddenly increase their energy consumption. Whereas in Ethiopia, you don't necessarily have this. I'm not aware of the same kind of diaspora type dynamics. So that might have something to do with it. But the low density versus high density population in the rural location is one of the key factors.
Brilliant. Thanks very much. So one of the things I think Stuart touched on there was about maybe looking to replace, say, diesel with tidal for, say, island populations. And a lot of the case we're talking about using renewables and cleaner, greener energy sources to replace diesel gensets or other fossil fuels. I guess one of the questions is how do we make sure that the communities working in those areas, the kind of the fossil fuel community is also on board with this transition and making sure that they are all working towards this as a direction as well. I don't know if anybody has any experience doing that or any opinions on that. I don't, but I have noticed you start to notice a lot of those kind of traditional oil and gas companies start looking at kind of offshore renewables, for example, because they have a lot of expertise in platform building and operating and maintaining equipment in the middle of quite difficult conditions. So they also have a lot of experience in this space. I mean, British Petroleum, BP, I think are no longer British Petroleum. I think they're just BP and are trying to remove that association with petroleum as they transition to a kind of a greener energy output. How much of that maybe is branding, and how much of that is actually underlying shifts? Maybe any opinions around that?
I think we've certainly seen sort of companies, like you said, the companies that have expertise in sort of things like support vessels and all that kind of stuff. That is kind of I guess it's sort of more I don't know whether it's the BPs and the Shells or whether it's the companies that operate the things that allow those companies to operate in the way they do. I think those companies are certainly potential for sort of for the shift to supporting. So, and again, it's in our very specific kind of field, but as you say, in the offshore renewable energy stuff, the people who are used to kind of, you know, taking vessels out to oil rigs can also take vessels out to offshore wind farms, things like that. There's a lot of kind of crossover stuff there, and as you say about the building rigs and the, you know, the guys who drill foundations and things like that. But I don't think those are the BPs and the Shells. I don't know. It's maybe not a nice thing to say, but do we need to kind of have those companies on board, or is their time done? And are there now new companies coming in, and those guys are out, and it's the new time? I don't know. I obviously don't rely on that kind of industry for my income, and if I did, I would think about it very differently. But yeah, I wonder if, as looking at it dispassionately and globally, do we still need those companies?
I think one consideration is that these companies have access to lots of expertise and money at the same time. So I think it's good to have them on board, but I think the driving force for them to be profitable is not necessarily the same way. So this is where I feel much more policies or would help, which could help drive these transitions. So it's just one particular field, but for air travel, for a long time I didn't understand, or I still don't really understand, why there aren't more fees introduced so that everyone would need to pay the carbon footprint related to the flight, so that could help these companies to develop more or greener or hydrogen-based fuels. So that's the question in me, why isn't that happening more?
Well, I think the aviation sector is a very interesting one, because it's not going to be easy for them to switch to batteries anytime soon, or hydrogen either, because they have to redesign the engine technology, and that's going to take the next 20 or 30 years, from what I've been told. So there's a transition between which they want to decarbonize, and the easiest way to do that is through sustainable aviation fuels. So the work that we've been doing with Ebury at Aston to develop, renewable kerosene from biooil. That's a typical way where we're saying, yes, we do need this sector, because they currently supply the aviation industry. They've got their storage depots, they've got the distribution. So, we're happy to work with fuel blenders. We're happy to work with, fuel manufacturers. If they are going to take our, upgraded biooil and renewable kerosene products and blend them into their, fossil-based products to reduce the, the amount of fossil fuels that, planes are burning when they're flying.
Brilliant. Thanks very much. I am just conscious of time, and I think we want to try and wrap this up in about 3 minutes. So maybe just very quick as a last question. Are there any particular dangers or threats that you think there's a risk that we might overlook, particularly in trying to kind of globally transition to clean energy? I mean, I know obviously, Matthias, you mentioned in your talk the how access to energy is obviously critical in so many aspects, in terms of quality of life, in terms of access to education, in terms of those various aspects. So we want to make sure that we're not limiting access to energy. But what are the kind of the main dangers, threats that you see that are really important not to overlook during this kind of clean energy transition on a global scale?
Yeah, I want to highlight something regarding that. I think we are overlooking the e-waste. So nowadays, e-waste is a major threat for all of us. And recently we had this G7 summit here in Cornwall. So we saw a few, a protest against this e-waste technology development, and how we can reuse the e-waste to the clean energy sector. So yes, I think the scientists or the researchers should think about that, how we can control the e-waste, and there should be a very clean policy which can direct us or the society, that how we can of course to move the society, technology is of course needed, but it should be in a sustainable manner. So that's a challenging thing. And another part is the trade-off between the cost and efficiency. So if you need a sustainable thing, very fast efficiency, but you have to invest a lot. thought. So that balance, the trade-off between these two terms needs to still in progress. So I think that should be a futuristic way, to get something benefit. And finally, of course, rather than strict to rigid to a particular subject or particular domain of our research, we should expand our hand to, make collaboration with not only for the science people, also for the humanities or the policy makers to, to make sure that whatever we are researching, that should be benefited for the society, and all the aspect of that work should be clear enough. So fundamental research is okay, and also a translational research is another part of that, but somehow we find there is a policy maker is nowadays is also important. So hopefully collaborative broad scale work is in future is indeed. Yeah, thanks.
Brilliant, thanks very much.
In the environmental impact, which I had a question for, I think this gives me the chance to answer that to you, but that's definitely something that needs to be considered and could be overlooked easily. And with perovskites, yes, it contains lead. And it's interesting with perovskite solar cells, which is like 2 or 3 steps ahead compared to like water splitting or photoelectrodes. So I think it's not yet such a concern. There's other problems to solve before. But it doesn't seem to be a problem at the moment. It's something that companies need to be very critical about and think about, and regulations, I believe, are very important. So there could be probably more emphasis there. At the moment, because of the very thin layer of the lead used, it seems to be fine. So there are companies trying to commercialize it. So I don't see it as something that's in the way of using perovskites in water splitting as well, but definitely something we should think about.
Brilliant, thanks very much. Just with the interest of time, I think that's a really good points that have just been brought up there, particularly around the waste aspect. I think it ties back into things, maybe into obviously what Gregory was presenting on right at the start about having taking that life cycle assessment and view of the materials you're using to enable the technologies which enable the transition and how it all feeds together, and clearly topics which have been touched on all the way throughout this entire morning session, and linking back again into the kind of the policy requirements around it that seems to keep coming up. Very interesting as well to see the points that Stuart was making around the kind of those human factors, that local knowledge, the kind of almost the human geography of it. I guess also linking through into Simon's work about how the needs are so different in different places depending on local aspects. So a big thanks from me for a really interesting session. Thanks to all the talkers, all the speakers for their presentations and their involvement in this panel. I think it's been really interesting, and I'll just pass back to Daniel, I guess, to wrap things up.
Thanks, Robin, and thanks again for chairing that session. I thought that was really interesting and topped off a really interesting morning of discussions that I feel like could go on, and there was lots of engagement in the chat. I just wanted to say a big thank you again to all of the speakers, and as well to the Cross-Hub Early Career Researcher group who put this together. So that's Amruta, Santosh, Lola, Kelvin, Ajit. Oh, I've forgotten names. I'm a terrible person. Rachel, and yeah, and I think this has just been a really fantastic start to our Supergen Net Zero Conference. As you will see in the chat, as I'm posting now, the next session is on equality, diversity and inclusion in energy research, and that starts at 1 o'clock after we've all gone away to have lunch and had a screen break. So I look forward to seeing you all back there then, and thanks very much for coming along. I really appreciate it.